he's also a fellow of Indian
National Academy of
National Academy. I'm sure you're likely to become my guest at some point. I hope so. Anyway, all yours.
Thank you. Uh, Thank you for the invitation and for the opportunity. It's a great honor to be present here. And also it's a great honor to present our work in the same session where Professor Ravi Nanjundia has presented, and he was my comprehensive examiner. He was my teacher. Of course, we are really thankful to our teacher for the excellent, for all the professors of IISc for their excellent guidance, teaching, even they provide till now. So what I'll be talking here mostly about data models and decisions towards end-to-end climate services and societal impact. So I'm trying to cover a broader regions rather than focusing on very specific works. So what I'll do is that, some of the introductory part, which has been covered multiple times. So I'll skip, I'll just give us brief intro and I'll directly go to the works which we have been doing. So of course, what I feel is that AIML, use of AIML, use of data-driven techniques, which has been happening in climate studies for quite long time. But I would feel that it is sort of a revolution when in science, the paper came on GraphCast and it also came on Science Cover magazine. Immediately after that, this has become really, really popular. And after that, we have been seeing a lot of papers which are specifically on application of AIML in climate science that has been coming at least once in 6 months in either in Nature or in Science. This has been happening. So this is, I feel this is one of the turning point or big revolution. And and at the same time, what we have been talking is that we are talking about, of course, data science, but at the same time, we have been talking about physics-informed machine learning. So this physics-informed machine learning, this kind of terminology was actually used in climate studies quite some time back in 2014, 2015, when Professor Vipin Kumar was leading one of the group with scientists from Oak Ridge National Lab and other national labs and from Minnesota and Northeastern University. They have been talking about this physics-guided machine learning around 2014, 2015, even before that. So, I mean, this is one of the figure which was used in 2024 paper, but I have been seeing Professor Vipin Kumar showing this paper for quite some time. So what he has said is that, when you're talking about climate modeling, there are certain areas where we have a lot of data. There are certain areas where you have very minimal data. In the same time, in terms of scientific knowledge, there are certain areas where a lot of scientific knowledge, there are certain processes about which we have a lot of scientific knowledge. There are certain processes where we have very minimal scientific knowledge. So, and we are somewhere here. So if we really talk about, we are somewhere here where science is incomplete as well as data is incomplete. And for that purpose, what is needed is what is known as physics-informed machine learning. So essentially, if you have a lot of data, we are going towards machine learning. If you have a lot of scientific knowledge, we are going for physics-driven modeling. And if you are somewhere here, then if you have some data, some theory, then use physics-informed machine learning. Then the question comes, what are the approaches? So one of the, there are multiple approaches, but 4 widely used approaches I am just focusing. The first one is emulators. So what does it mean by emulator? In the morning, we are discussing about how fast we can generate the forecast. And we know the global models are running. Global models take some time. They provide the forecast. As soon as these forecasts are available, then if you start, let's say you start running a regional model, then regional modeling will take their own time. It will generate some results. Then let's say if you're applying it to a flood model, then flood model will also take their own time and generate results. So by the time you'll get the impact-based forecast, the already flood would have already happened. So it's not really very useful. So for this purpose, what is being considered is that, let's say if you have already trained machine learning model that can generate the forecast quite fast, you don't need a high performance computing facility to really generate those forecasts, that is good. And for that purpose, what is being said is that, let's say if you have a regional model, let's say if you have regional model, you run it for multiple times, you have huge simulations that has been generated, why not use a machine learning model to train those input and output from a regional model or from a flood model or whatever. And those are called emulators. And those emulators you can directly use whenever the global forecast system output is available. That is called emulators. And there are significant number of papers which are coming in terms for emulators. The second one is, when you are talking about calibrating a model, data-driven model, and then really applying for some condition which the observation hasn't seen, or we haven't seen that sort of condition in observation, then the model may extrapolate in a different ways. But your physical knowledge tells that, look, this is not possible, or there are certain physical constraints. Can you really use, based on those physical constraints, can you really use some loss function, some penalty in the loss function? And that is known as, you are training the model, but you are using your physics as a constraint. So that is known as physics constraint machine learning training. The third one is, it is also very interesting. What is being said, so it's mostly used now in soil moisture modeling. What is being done, let's say if you have a larger village where there are, let's say, thousands of farms are there, but you have only 50 farms, you have soil moisture sensors. For other farms, you do not have any observations or anything available. So, but you have to generate high resolution soil moisture data or high resolution hydrological data. How can you do that? So the idea here is that for those regions for which you do not have the soil moisture data or anything, but you can still use a physics-based model with whatever knowledge is available and generate some simulations. So merge these physics-based simulations as well as observed data together, generate that big field, and then train a machine learning model. And that is known as physics-based, so essentially the physics-based model output are used as an auxiliary data along with observations. So that sort of things which has been now widely used in soil moisture training. And of course the fourth one is foundation models, where we are talking about foundation models for different processes, even global models, we are talking about Aurora kind of models and so on. So there are, and also now we are talking about neural GCM, where we are essentially talking about fully differentiable AI/ML model for global circulation. So that's another revolution which has taken place in 2025 very recently by the Microsoft team. If you are looking at it, I'll always say that every 6 months there is one or another paper in Nature or Science, and those who work in climate, we are finding it really difficult to catch the pace. And interestingly, this image is also generated with ChatGPT. But that's the reality. And for that purpose, we alone cannot really solve this problem. We have to collaborate with computer scientists. So, one of the uh, uh, in 2010, when I was at Oak Ridge National Lab, there I have seen that a lot of computer scientists, they were really interested in understanding climate and working on climate modeling. Because I have seen many scientists in Oak Ridge National Lab, they are interested in understanding climate, and then finally they have become like a climate modeler or climate scientist. And also I have seen many of in the present days also, at IIT Bombay, I can see that a lot of students in computer science, now they come to us and they say that we'd like to do a project on climate, which is something really good which is happening. This is what we can see. Last 4 years. In fact, I'd say that after 2023, this science paper, I've seen that a lot of faculty from computer science, they are really interested at IIT Bombay to work with climate scientists. So previously also there were collaboration, but this has strengthened significantly nowadays. So other than this prediction, one of the other things which has been extensively now used in climate, what is known as causality, causal discovery approaches. And if you go back a little bit, I can remember in 2010, 2011, when Professor Praveen Kumar from University of Illinois Urbana-Champaign, he started developing a method called process network with using the Shannon's entropy, transfer entropy kind of concepts. And he was developing a lot of work. Then one of their paper came in PNAS, where they had tried to understand intensively managed landscape AD modeling. So essentially trying to understand how much photosynthesis is happening, how much carbon flux is happening, how much energy flux is happening, and they tried to understand how the micrometeorological variables are impacting these processes. And then in 2017, there was a paper which was done by Jacob Runge, and they developed a method which is known as PCMCI approach, Peter Clark momentary conditional independence, where they have considered the Peter Clark approach to, let's say if you have a climate system which has n number of variables and you do not know how are they really connected. So they first use, based on correlation, partial correlation and so on, conditional correlation, they first create an skeleton of the causal structure which doesn't have a direction, which is Peter Clark algorithm they use, and then they take the time dependence causality, causal graph using MCI, where they do a lot of conditional causal mapping. That means, if you're talking about X, if it is driven by Y or not, so they are trying to find out the input that is coming from past of Y, conditional on past of X and past of other variables. So that's the way they develop this PCMCI approach. And this method was useful, and they have shown that, this group has really shown that this work is really useful for climate system, and at the same time the codes were immediately made available. So the good part is that immediately we could see that huge number of papers came used in lot of nature food, nature communications. Suddenly all the big venues have been flooded with papers which is for understanding the causal inference. And I mean, there are something which came out from here, that is, physics based approaches are, because people have started understanding that physics are always not adequate to understand all the processes, I mean the present current scientific knowledge. So we need to take help from data to understand some of the causal discovery or causal thing. And the second thing is that, if that shows the power of open science. That means when some codes are available, some methods are available, yes, people use that, and there are a lot of applications you can see. Now, one of the things where I believe that many of the climate papers really failed, and some of the papers are in Nature Communications and so on, is that they sometimes made mistakes for not really understanding the assumptions. And that was one of the major issues. For example, first one is causal sufficiency. There should not be any hidden co-founders. Second is causal Markov chain. That means be depending on past, then faithfulness, stability, stationarity. I think these are some of the algorithms which are there in many of the causal inference approaches. No contemporaneous feedback and sufficient data length. And also the other problem is that I have seen a lot of applications of causal discovery approaches for monsoon rainfall, where June, July, August, September data again stitched with again next June, July, August, September. In between data were removed. So essentially your causal chain is getting breaked, but this discovery method is applied and the conclusions came out. So those are really some of the problematic things that has happened because of a blind application of this method. So we have to be a little bit careful about it. So I'll focus on one of the paper. This was one of the paper which came in 2023 in Nature Communication. This paper said that, if you are considering the drought condition, that means if you consider it in a PDSI or rainfall deficit condition, they found that they are causally connected, and the major hotspots are these regions. So yeah, so they use complex network and they found the degree centrality, and they have found that these are the main drought hotspot over this region, and they drive the droughts all across the globe. So there was no story, so it's just purely based on data they have found it, and this came out. And the second thing what came out, which is even more dangerous, is that they said that if you consider the distance of these links, I mean spatial distance associated with the links, they said that highest spatial distance you are getting over the southern hemisphere, where the northern hemisphere does not have that much distance. This is quite obvious because southern hemisphere has very little land space, so all points are far away from each other. So of course it will happen. These are quite obvious, but that's the way the artifact has came out. There are major conclusions. So one of my students, Tejasvi, took that, and Tejasvi started reading that paper, and I remember one fine morning he told us, sir, these results are completely model artifact. I'd like to do it with ocean and land together and would like to find out what's happening. And when he did that, of course, the quite obvious results are come out. This is the region which affects, I mean, this is essentially the equatorial Pacific and this. So that's actually affect the most of the droughts over the globe, and mostly ocean drives major drought conditions across the globe. So essentially, these are quite obvious things which are happening, but you know, but this was completely lost because of the new knowledge which has come, which is not really correct. So we have to be very careful. The second thing is that one of my student, Elizabeth, she was quite interested in understanding, of course, we are talking about causal discovery methods, but how robust are these methods themselves? So that was the question she was trying to pose. And so Elizabeth, myself, and Professor Arup Ganguly from Northeastern University, some of us are working together. So what we started doing is that we picked up 4 independent, normally distributed random variable x, y, z, w. And then we started finding out their causal association. And what we are finding is that these are 2 methods. One is with fixed bin and one is with kernel density method. When we applied transfer entropy, we found that some of the wrong links which are appearing, and they are statistically significant. So we started thinking what's happening. So then we thought that yes, it may happen, this kind of links may happen by chance, but how to really understand if such links are really reliable or not. Here we know that they are not, they are independent of each other, but in real applications we do not know. So then what we did, we picked up a data set of, let's say, 1,000 and then took subsamples, and they may be overlapping with each other and so on, because otherwise you cannot generate multiple subsamples. And all these multiple subsamples, we are trying to find out the appearance percentage. And then we have used a cast index, which came in physical review very recently. So we used some kind of an index, we developed an index. That index is taken care of so that the lower appearance percentage means higher cast index and so on. And when you are saying that cast index is less than 0.1, we are saying that the links may be considered in some sense robust. So some sort of a quality of the method or significance we can consider, and we found that that is actually able to, with that we are actually able to eliminate some of the wrong links. Then then we went back to another paper which is quite well known paper since around the time of 2017 2018, around that time there is a group from ETH Zurich led by very quite famous Professor Shania Seneviratne. So they have been working on a work which tells us that it talks about carbon growth rate. Carbon growth rate is essentially means that if you are taking at every year's carbon dioxide concentration globally, take out their difference, remove the trend, then what is the variability? And what her group was claiming is that this has a very strong correlation with the total water storage which you are getting from GRACE satellite. So GRACE is a satellite. With some gravitational method, they compute the total water storage, and they found that there is a very strong correlation. They immediately said that this total water storage is driving the interannual variability of carbon growth rate. Before that, there was another paper which was again in Nature. It was in 2016, 2018, 2015. There was a paper by Jung et al. They said that vapor pressure deficit actually controls the vegetation productivity. So, but this group said that no, this is total water storage which is actually controlling the vegetation productivity, and that impacts the interannual variation of carbon growth rate. And after that, there is another Nature paper they published. Actually, they published 2-3 follow-on Nature papers where they kept on proving that total water storage is one of the factor that is affecting, using different models and so on. But what we did, we have used simple causal algorithm, whatever methods we have. One is PCMCI, one is transfer entropy, but with the robustness check. And when we did that, what we found is that whatever major links which should come, like precipitation to total water storage is coming, temperature to VPD is coming, even photosynthetically active radiation to CGR, they are coming. All these links are coming, but total water storage to CGR is not coming. So then we realize, of course, that means that correlation is not causality, and it's quite well known, but somehow they kept on getting published in Nature and so on. But that's one of the cases which we have found. So we have to be little bit careful. I'm not saying that the conclusions are wrong or anything, but I'm saying that through data they tried to prove, but through data it cannot be proved just using data. So that's the point. And we have to be a little bit careful when we make. Huh. No, they are saying that more terrestrial water storage means more vegetation. So vegetation is not under stress. So they can absorb the carbon dioxide. So it's a negative correlation. Yeah. Yes, yes. Exactly, exactly. So there it's a much complex thing rather than just a simple correlation. That was our point we tried to mention. Hmm. Yeah, so yeah, they have found negative correlation, but at the same time, it will have, if the temperature is more, the VPD will be more, and then that will impact the vegetation, and that also can have. So it's a quite complex phenomena, and it cannot be just computed based on correlation. That was the point. So they said that we are removing the trend, so that so that's the way they are saying. They're not considering. They're keeping it pretty simple. Yeah, exactly. That's the point. What we tried to say is that it's quite complex, and just based on correlation, we cannot. Yeah, exactly. So what they're saying is that if you remove the trend, the increasing part is gone. So it's now the interannual variations which is driven by vegetation. That's what their conclusion. And vegetation and total water storage drives vegetation. So yeah, exactly. That's the point. But oversimplification and yeah.
Basically, you are telling that causation is not, correlation is not causation.
Yes. So these are the things. Now what we tried to do, so Tejasvi was interested in understanding, because we have been talking about interlinking of river basin, and Tejasvi was working on land atmospheric feedback. So Tejasvi was telling that, okay, we know that if you do something, if let's say if you irrigate so much, or if you do something, it has some feedback to the atmospheric processes. So, but now through interlinking of river basin, let's say if you pick up some of the deficit basins and keep on irrigating, will that have impact on any atmospheric process or not? So the idea here is that, and then that can affect the atmospheric condition and hence the land variables on the donor basin as well. So that was the point. So are they really causally connected or not? So we started looking at it, and what he found is something very interesting. What he found is that if you're talking about land variables of one basin, it will have land atmospheric feedback. So for the same basin, it will have impacts on atmosphere. And atmosphere doesn't have a boundary. Land has boundary, river basins have boundary, so water cannot cross the river basin boundary, but atmosphere may not have a boundary. So atmosphere can have impacts on the neighboring basin. And if that is happening, so neighboring basin can also have impacts on the land variables. So his point was that, yeah, whatever you are doing, whatever you are planning on land, you also have to think of the land atmospheric feedback very carefully. In fact, I would say that land, atmosphere, ocean, all of them has to be considered very carefully. But here he is just focusing on land and atmosphere. And what he tried to do, he tried to run a WRF model, where he is considering, I mean, this is from the government's report on river interlinking, what are the regions which will be extra irrigated. And he added those extra irrigation and ran a WRF for multiple years, I think 20 years, and checked the September rainfall, where the land atmospheric feedback is quite high because of that. And then he found that there are certain regions which are consistently getting higher or lower rainfall, with statistical significance. Of course, this has a lot of limitations. We know that there are butterfly effects, etc., etc. But what he's trying to mention here is that if you are really talking about any kind of change of planning or management over land, you have to consider the holistic view rather than just the view of that specific watershed or specific river basin. So we published this paper in Nature Communication. So now, that was more about the causal part, but I will now go a little bit to regional modeling and bias correction. Of course, we have been talking about bias a lot. We know that climate models have their own bias with respect to the observed data. So we have to do bias correction. Now, when it comes to bias correction in 2010 or 2011, around that time, Lee et al. Came out of a method which is known as quantile mapping based bias correction, which is very popular. In fact, IPCC Year 6, many assessments were done based on quantile mapping. What it tells is that if you have an observed CDF and if you have a simulated CDF, so let's say this bold line is the observed CDF and this dotted line is the simulated CDF. What you have to do, let's say for simulated some value is there, you go to the simulated CDF, pick up the CDF value. For the same CDF value, go to the observed CDF and find out the value and replace that with the observed CDF value. So essentially, you forcefully merge the CDF of the output with the observed condition. It's a forceful merging. So, and it has been widely used because it is CDF, cumulative distribution function. So, yeah. Yes, exactly, exactly. And that has been widely used. Quantile mapping methods, everyone uses that, and that's one of, so Bikram, one of my other student, Bikram, so Bikram said, we have to be careful what exactly we are doing. So he said, okay, we have observations, we have GCMs, then we'll consider, another condition with the same resolution as GCM, we'll consider completely random number and then apply bias correction. And if you apply bias correction, for GCM bias correction, for random number bias correction, both are working same because you are forcefully, as you are saying, that you are hammering it to, merge it. So, of course, it looks funny, but this is very serious problem because the serious problem is here. GCM has their own properties and you are doing bias correction. Now, randomness has its own property, but you are making sure that entire property is gone. That means you have spent a lot of computing time, do the simulation to get certain property or something, and then you are making sure that you are removing everything so that it will behave like observations. And that we felt is not a very straightforward thing, and that we have to be very careful. And the other point is that when we talk about bias means systematic error. So essentially we have to remove the systematic error, not everything. But when we check the corrected part after this quantile mapping based bias correction, it's all white noise. So errors are actually white noise. That means you're not really removing systematic error, or you're removing systematic error, but more than systematic error, the other part which you are removing, the bigger part, which are essentially random noise. Just to, so essentially you're distorting the properties, and that is one of the major problem. So then what he has found is that, of course, he has applied it to many other many other areas. For India, what I'm showing his own results. So this is observations of dry days, and this is with for the observed period, and this is with original CAN ESM2 results. They are somehow this case it was nicely matching, but when you are applying BCSD, you can see it's getting amplified. So there was a 2017 Nature Communication paper. I cannot remember the name of the authors. So what they have shown is that they have started saying that if you are applying BCSD, be very careful because that may amplify your climate change impacts. And he was also getting the same. So at the same time, he has also added that, if you apply bias correction on anything, its property will be gone and you are getting something new. And interestingly, it was highlighted in Science, soon after this paper was published, and it was says that all the science that goes into building these Earth system models was rendered meaningless because of this bias correction. So that is what we have to be careful. So I'll now quickly move. So what Bikram tried to do is that he wanted to develop a method which was earlier developed method YNet, which was a very famous KDD paper which won the award and so on downscaling. Yes, this is one of the examples where computer scientists were thinking of downscaling and they are developing methods. And what Bikram did, Bikram tried to use the method with extra more weights for extremes, and also because extremes are poorly modeled by the downscaling models. And also India has, at interseasonal scale, it has some east-west asymmetry. So central India, when this is high rainfall, northeast of when this is low rainfall. That part we are using some soft constants. And when we did that, if you look at it, of course, there are multiple methods. This is with IMD, this during the active period, this is break period, this year interim active and break period. Now, if you are applying BCSD, what you can see is that in active, all are becoming active. So essentially, when you are applying, taking a large data and apply BCSD, but if you are looking at a specific time period, active period or break period, your things are getting distorted. But somehow these machine learning algorithms are able to conserve this east-west asymmetry. So they are not, I mean, so essentially it's much better than this forceful hammering. Of course, it has to be because there are a lot of things which are going on, but this is something what is very important that we have to be very careful just before just applying BCSD. Now I'll go to some of the applications which are more on weather scales. So one of the first applications I'll be talking about weather smart agriculture. So in 2019, just before COVID, we got a student, Adrija Roy, and she was very much interested in working with farmers. So what we started, we started visiting one of the region called Nasik, which has vineyards and a lot of grape farmers are there. So, and many of them have soil moisture sensors, they're quite rich. So when we ask them, you have soil moisture sensor, how do you perform the irrigation? Do you use weather forecast? They said we don't use weather forecast. We just use the soil moisture sensor, and based on soil moisture value, we irrigate. Then we asked why. Then they said that, we know that weather forecast is for coarser resolution. I'm more interested in what is happening on my farm, so I'm not interested. Then we'll say that, we told them that, look, we can understand that weather forecast is for coarser resolution. We do not want you to really use us for your fine resolution farm, but what we can tell you is that even at coarser resolution, whatever added value you are getting, that will be useful for fine resolution. Then they asked, can you develop a method for that? We'll be happy to use that. So what we did is that we have taken the past forecast, which is hindcast, and past rainfall, and we develop a conditional distribution of rainfall given the forecast. So once we have the conditional distribution of rainfall given the forecast, then let's say if I know tomorrow's forecast, then for tomorrow we can generate 1,000 ensemble kind of thing based on the conditional distribution. And we have the real-time soil moisture for today. So what we did is that we developed a farm scale, very simple eco-hydrological kind of model, which takes care of vegetation stress and the soil water balance. And then we ran a stochastic optimization model, which has a probabilistic constraint that the root zone soil moisture will be less than a threshold with certain probabilities, and this probability farmers can fix. And we have to minimize the water use. If you ran this optimization model, then they found that they normally, some of the farmers irrigate once in 3 days, some of them once in 7 days, and so on. And they found that we have checked for few stations, and they found that 10 to 30% of the water can be saved if they use weather forecast. Of course, it is obvious, but they did not know how to really use the coarse resolution information or added value for the fine resolution. And of course, then we got a patent on it, we published in WRR and so on. But the interesting part was that they immediately asked us that, next day is fine, but we are more interested in 2 weeks in advance, how much water I have to arrange. And that was one of the interesting points they were interested. Then we talked to Dr. A.K. Sahai, and he was kind enough to provide all the hindcast, which was, I always feel that providing hindcast is very important if we have to make climate services really applicable for community, for every pupil. So Dr. Sahai realized that, and he made entire hindcast available, which is run at IITM Pune. Yes, yes. No, we didn't. We kept it very simple because we wanted to, because those farmers, they also wanted to understand what exactly is happening. So we kept a pretty simple method. So here also what I did, we just used the weather generator of hidden Markov model. So from this limited ensemble, we have generated huge number of ensemble. And then we use the same approach. And when we use the same approach, what we found is that water saving is possible. And at the same time, proper water management decisions can also be made 2 weeks in advance. Beyond 2 weeks, it's not working very well. But up to 14 days, it's working very well. And they said that's their time. They say that we'd like to know 10 days in advance how much water we have to arrange. If we get this information, that's the best thing we need. So now the real challenge came. The real challenge was that, when you're talking about soil moisture varies like anything. I'll show some of the figures. Because of the way farmers irrigate, the way farmers use their land and so on, it changes like anything. And not every farmers can afford really soil moisture sensor. So the question here is that how to really get information at every farm. You cannot get, and the satellite footprint is quite large, and they give at surface level. So what we tried to do, Adrija started developing a simple approach where she wanted to cluster similar kind of farms into one cluster, and for each of the cluster, she is finding that if at least one sensor is available, at least for one farm. And she developed a machine learning algorithm for that and applied it for other farms. And that's the way when she worked, she found it's working. Of course, not as good as in situ sensors, but some information, something we are getting. Then we started looking at soil moisture downscaling algorithms which are available. One of them was one of our own colleague, Kartikeyan Lanka, who is now in at IIT Bombay, but he developed this method when he was in Texas. So the interesting part in the US is that they are really large farms and the methods are quite systematic. So it's easy to do downscaling. But for India, I'll show you, within 10-kilometer radius, we picked up 4 regions, 4 farms, 4 small farms. And if you can see the variation difference, and they are essentially rich farmers, they belong to a same cluster of grape farmers. But if you take the soil moisture values, specifically for the dry period when they irrigate, there are huge differences. So if you just go few meters, let's say 500 meters, you will find entirely different soil moisture. So soil moisture cannot be monitored under control condition. It has to be under real condition, but at real condition, there is so much of variation, you cannot do anything. So it was really, really very challenging. The other part what we have found is that there is very low correlation. Within 5 kilometers, the correlation becomes negative or very close to 0. So absolutely no correlation, and hence it's very difficult to generate a soil moisture map or develop something. But one of the things what we are now asking ourselves that, can we really understand human? Let's say we start talking to human, develop some method by which we can get a lot of crowdsourced data, and at the same time, if we get some socio-economic information and farm size, can you incorporate them to understand some sort of a human behavior and incorporate them in soil moisture mapping? So this is something which we are planning, and some of our students like the idea. So they pitched it as, they are going ahead for incubation of this. They won the Climate Entrepreneurship Award. So their idea is that creating that interface by which they will collect the data from farmers, they use these models and give a good output for an irrigation advisor. So that sort of things they are planning to do. So this is something which is happening at IIT Bombay. Yeah. Yeah. This one you're talking about, huh?
Dry periods, or when it is raining also, this is the case.
Even when it is raining, you can see the differences. So this is during the break period. Of course, during rain, even during rain also you can see.
Saying that different farmers will irrigate in their own way, and there will be so much of variability. But when it is raining and the soil moisture also doesn't vary too much, how to justify it?
It can be slope. Just a little bit of change in slope, it can drain the water in a completely different way. So the slope of the farm is also playing a major role. Essentially, even within a farm, if you put the soil moisture sensor on one end and put the soil moisture sensor on the other end, you'll get huge difference because of the just slope. Crop pattern also has a lot of variation, but this is the same crop as grape, same kind of grape, we have made sure, but even just the slope change will make a huge change. Not much, not much. Even with a low slope also there has been a lot of change. So this high resolution soil moisture variation is still something. It's much more complex problem, but it is not really being addressed in a proper way by hydrologists. Yeah, I'll just quickly talk about the Mumbai flood thing. So for Mumbai flood thing, I'll not go into the flow chart. So I'd like to mention that 2015, after the Chennai flood, the principal scientific advisor then Dr. Chidambaram came to us and asked us to develop India's first real-time end-to-end urban flood forecasting system. So there were 8 institutions of 30 scientists. We all worked together. In 1.5 years, we could develop this framework and we could develop the model, which transferred the technology to National Center for Coastal Research, which is now known as CFLOS, Chennai Flood Warning System. But what we did, we started looking at Mumbai, which is even more complex because of the high spatial variability of rainfall. So I'll refer to one of the paper which was written by Shupantha Pal, where he showed that if you could take 15 minutes rainfall, within 5 kilometers, the correlation vanishes. it goes below statistical significance. So that sort of variability we are talking about when we are talking about Mumbai rainfall. But there is an interesting feature, that is there is a horseshoe pattern in this region which receives very high rainfall, and this is the low elevation region because this is the Sanjay Gandhi National Forest, and this is around 0 elevation, this is around 500 elevation. So this is a hilly region and this is the coastal region. So some local scale orography is probably playing a role because of which we are getting this. So what we tried to do, we tried to develop a downscaling approach. So Mumbai has the advantage of multiple automatic weather stations which are available with, is jointly owned by Brihan Mumbai Municipal Corporation, BMC, and Ministry of Earth Sciences. So there are multiple stations. So what we tried to do, we tried to cluster the stations. So the same rainfall pattern stations can be clustered together, and one station from each cluster can be used. And then we developed a CNN based model. It's a pretty simple model. We have used the GFS forecast and use a CNN, and every 15 minutes they provide rainfall data. No, other data also they provide. Now they started providing temperature, rainfall, and humidity. So when we started doing it, first we applied CNN. It was working very well, but for extremes it failed. Then what we did, we picked up that CNN, we did some transfer learning only for extreme days and developed another model. So what we did, if the GFS says its chances of extreme, then we use this transfer learned CNN, otherwise normal CNN. And when we started applying, I don't know. So when we check this, this is the NCEP GFS hit rate, and when you are using it CNN, it is improving, but when you are using this combined approach, then it's quite significantly improved. Then this is about false alarm. The false alarm was quite high with GFS, but when you are using combined approach, it's working better, much better. Then what we did, we have made the performance, we have gone up to 3 days, lead day 1, lead day 2, lead day 3. So you can see that correlation coefficient is improving, RMSE is reducing, as well as threat score, which is a combination of hit rate and false alarm. This is also increasing, specifically for lead day 3, where both of them are not showing much of skill. Its CNNTL is working quite well. Then we have shown it at station level. So essentially, forecast is for rainfall for next 3 days and rainfall forecast. And the input is the GFS forecast of humidity, temperature, precipitable water, wind velocity, and so on. So meteorological. Yes. So then what we want. So and there was a paper. So of course NCCR has come up with another model for Mumbai that is known as the iFlows. iFlows use NCUM model output from NCMRWF, and NCMRWF had a paper where they have shown the equitable threat score for certain years. So we computed our equitable threat score. Of course, it's not like comparing apples and oranges, because that's a global model. It's much focused trend region, downscaled model. But still, what we are finding is that with that, the performance is quite improving. So what I'm trying to say is that if you do a site-specific downscaling, performance really improves and it really adds value for application. This is regional model. That's what I'm saying. Income is a regional model. Then, yeah. Regional model. Okay. Fine. At those stations. No, we are doing that in daily interval. This is about daily. I'll show you about hourly interval also. So then what we did, we have set up a few sensors in Mumbai. That was very challenging task. We have spent 2 years to talk to BMC, to electrical. It was a challenging task, because we realized that installing a sensor by an academic institution is really tough. So then we started collecting a lot of crowdsourced data. So first we started with Twitter. Before Elon Musk took over, Twitter data was available, so we could easily get the API, and from there we could collect the crowdsourced tweet data. And we thought that even a lot of tweet data can be just noise. So just to check, we started talking to some of the NGOs, and they have volunteers. They started collected data. We started matching. So we used to do this kind of matching. For example, July 5, 2022, from tweet we are getting, these are the regions which are getting flooded. And then we have, this is the volunteer data, VGI data. We found that a lot of volunteers are reporting that these regions are getting flooded. And this is the elevation, which is low-lying area. And if you check that day's rainfall data, this is the region which received high rainfall. So merging all of them, we realize that, okay, this crowdsourced data is not bad. They are providing good information. So that is one of the things. The other thing is that we also have developed radar-based nowcasting system using UNet. So what we did is that we talked to RMC Mumbai, and RMC Mumbai shared the past radar data. With that, we developed this UNet model, and then for next 90 minutes forecast. So essentially, looking at the past velocity vectors and the reflectivity, and based on that, for next 90 minutes reflectivity. And then we set up this model at RMC Mumbai's office, because real-time radar data, we should not get the access, academic institution. This is what we realized from them. So we set up the model at their office only. And this is some sort of results. What we are finding is that it's working very well up to 90 minutes. And this is the 3-day forecast for 2024. This was run on real-time operational mode, but experimentally operational, because we cannot do operational thing. We can do only experimental, which we did through our web portal. And except one day, for all the extremes we could capture properly for 2024. And then we started running a flood model. You can see how flood is developing. This is on 25th September, one of the days of the last monsoon, when it was extremely flooded. 200 mm rain happened in 7 to 8 hours. And this is the way we could develop flood model. And these are some of the validations which shows that, of course, even for flood model also there is some bias, but we can at least tell that what at the time when it is getting waterlogged. TU flow. Yeah. So, and then in 2024, through this web portal, we have connected to people, and we could get a lot of forecast correctly. Specifically for 25th September forecast, there was no alert as per BMC. And BMC then found that we stated that 24th September, that on 25th September, there are chances of extremely heavy rainfall. So that probably that one event that BMC Additional Commissioner Mr. Abhijit Bangar liked it. So next season, this season, he came to us before the season, and he said that he wanted to use the IIT Bombay model for their. So he connected with the stormwater drainage people, and then we started working together again. And they are only with started working with RMC Mumbai as well. So this is our Mumbai flood web portal 2025. The web portal, if you put mumbaiflood.in, you will see this rainfall, nowcast, flood model, everything is available. So if you click on rainfall, for every station, you can see for next 3 days forecast, as well as we provide the past forecast. And also this is from BMC, last 6 hours, what is the observed rainfall. We do nowcast. Nowcast model output were available, but now IMD has requested that it has to be password protected, because nowcast output we cannot show here. So we are making it password protected. Now flood models, water level, I'll show one by one. So this is the forecast for 18th and 19th August. And 18th and 19th August, we received very high rainfall. You can see that nearly 200, more than 150, more than 200 rainfall we received. And this is our forecast, which was on 17th August. We provided this information immediately to BMC on Sunday afternoon to the stormwater drainage section, that you have to be careful and you start cleaning, because for BMC it's very important that they have to clean the stormwater drainage. There are a lot of plastics and other things. They remove that, and if they make their pumps ready one day in advance, then the flood resiliency is quite good. I think BMC is one of the best in terms of flood mitigation. So, and then this sort of nowcast information we provided during that time. Now we cannot do because of data constraint and other permission issues. And we showed that how the high reflectivity band is moving. An interesting part is that a lot of people actually followed. Around 60,000 views were there in our website. And this is the way we get the crowdsourced information. So we have kept it pretty simple. Someone can just click their current location. If they see waterlogged, they can put their height. They don't have to measure the water. And they can say qualitatively, this is ankle length, knee length, waist, or full body kind of thing. And they have to just submit. And then it will calculate. They know what fraction is it from human body. And you could see that these many people, lot of people have actually participated in providing this. This is for one day. This is on 19th August, on Tuesday, when extreme rain happened, and a lot of people have participated. And you can see in 1 hour, the water level doubled in one of the, you know, and then other thing also, we have provided the transport stress. That means railway stations, what are the stations which are getting very extremely heavy rainfall? That information we have generated. In fact, we have showed in one of the very recent paper which just got published that if you add crowdsourced information, the the network efficiency loss, essentially using the network theory, you can find out transport network efficiency loss that can be quantified. And if you add this extra information, you can predict much better way the network efficiency loss. And this is the flood model. So 19th August morning, because BMC was interested in understanding what are the regions will be waterlogged. And as I said that we are running flood model which takes longer time. So we have to, I'll just complete. We have to use the emulator to simulate that, but we did not complete the emulation part. So what we ran the flood model which took time. On 19th August, we told them that this is the condition, but this is the regions which is probably getting waterlogged. And interestingly, somehow it matched. Of course, it's sometimes very unlikely that this will match very nicely over this, but that is the region which actually started getting waterlogged, and somehow they made their pumps ready, and that could save. So immediately on the next day, BMC Additional Commissioner in the press conference, they acknowledged IIT Bombay's effort, and they have specifically mentioned, and that we could see that in Times of India and many newspaper has reported that. And more interesting part, which we felt really nice, that science also highlighted our efforts for Mumbai flood. So yes, so this is our Mumbai flood team. This is all students. There are two faculty. I mean, Raghu and I, we are kind of mentoring, but we have learned from them, from the students and staffs. Students, staffs, they work together and they develop the system. So it was a great learning experience from them. So that is something I'd like to share. And finally, thanks to all my students who have worked with me. And it was a great learning experience working with students and knowing their work from them and so on. So, and thank you for the opportunity.
Thanks, Subimal, for a very nice talk. But I think we are running a little late, though, and you are, I guess, fairly active on social media. So those who want to kind of have questions, I'm sure many of you have questions to him. You can either email to him or contact him.
Definitely.
Sure.
Yeah.
Oh, sure. You're leaving now, or
no? I think 4:30 is fine. Right?
Okay, so maybe during coffee break they can ask.